Introduction to Delta-Wye Transformer Connection, Part 5. In Part 5, we're going to perform phasor analysis on the Delta-Wye Transformer connection and look how the square root of 3 and 3 degrees phase shifts comes into play. So, okay, this is what we illustrated in Part 4. We did a nodal analysis on Node 1, Node A1, and Node B1 and Node C1, and look at the relationship between line current and phase current. And these are the equations that we came up with. Line current A plus phase current C is equals to phase current A, and line current B plus phase current A is equals to phase current B, and line current C is equal to plus phase current B is equals to phase current C. So now we're going to evaluate this particular equation and look for a phasor diagram perspective. Okay, let's rewrite the equation into something that makes a little more sense. Okay, so all we're going to do is take the phase current here and move it into the other side. We're gonna move it here. Okay, so let's rewrite this equation and solve for the line current A. So line current A is equals to phase current A minus phase current C, and line current B is equals to phase current B minus phase current A, and line current C is equal to phase current C minus phase current B. So now that we written our equation like this, let's define our phase value. So our phase value are the currents that are flowing through our windings. So we're gonna define phase A and phase B current and phase C current. So we're gonna define this current and create a balance system. So let's say that phase current A on the primary side is phase current A is 1000 amps. It's equal to 1000 amps at 0 degrees. And phase current B is equals 1000 amps at 240 degrees. And lastly is phase current C with equals to 1000 amps at 120 degrees. So now we're going to draw these phasors. Remember, these phasors are just currents that are flowing through the primary winding. Here. Keep in mind that we're trying to solve. We're performing the phasor analysis because we want to relate this line current here with actually this phase current and this phase current. So we're doing a nodal analysis on node 1, node A1. And what we're actually trying to solve with our phasor diagram is this particular equation here, this one. We're trying to find out what this line current equals when we subtract our phase current A minus phase current C. So what we have here is what our phasor diagram looks like. Here, this is the reference line. This line right here at 0 degrees marks, this is our reference line. And this phasor that's going through this reference line here, which is at 0 degrees, this is our phase A current. Here, this is our phase. And what we're saying is that from this origin point here to this point here is at 1000 amps. And the angle is at 0, which is the same direction as our reference line. And this phasor here, this is our phase B current. And from this origin, here and here, this is 1000 amps. This is our phase B current. And the angle, which is 240 degrees of what we defined, this angle is from the reference here, the line going in a counterclockwise. Until we're gone 240 degrees. So this angle is 240 degrees. This angle. And lastly, this phasor here is our phase C current. This is our phase C current. And again, from this origin to this end tip, here is 1000 amps. And the angle from the reference line here, going counterclockwise 120 to get this phasor here. It's 120 degrees. And that's for part 5A. Now we're going to take this phasor and subtract phase A current with phase C current, and then look at what our current A looks like. Here is phase A current and here is phase C current. Now if we want to perform phase A current plus phase C current, we will do this what we call the head to tail method. And how that works is very simple. We would pick up phase C current and add it to the head of phase A current, and the resultant vector starts from the origin and go towards the head of phase C current. So this right here is our resultant vector. This resultant vector equals phase A current plus phase C current. However, this is not what we want. What we want is to equate this equation, phase A current minus phase C current. So let's clean up a bit and put it back. Okay, because there is a minus sign associated with phase C current, we have to pick phase C current and rotate it 180 degrees. So phase C current becomes like this. So phasor here is negative phase C current. And now let's pick this up again and connect it to the head of phase A current. Now we're going to connect it like that. And now the resultant vector starts from the origin and ends at the head of negative phase C current. Now notice the resultant vector is longer right now, right? The resultant vector represents phase A current minus phase C current. Now believe it or not, this phasor diagram actually represents this equation here. And this resultant vector is actually representing this line current here. So we're saying we're comparing line current with phase current A. Now remember, this is phase current A here and this is line current here. Let's label a little better. Now we see that line current is a lot longer than our phase current, right? This phase current here and this is our line current. So the magnitude of line current, which starts from the origin and ends up at the tip here, and this is larger than our phase current. In fact, we have compared the two. We will find the line current is actually a square root of 3 times larger than 3 phase current. So if we take phase current here and line it up with our line current, we would be at this point here. But when we have to sketch it, or we have to multiply it by square root of 3 or 1.73 to make it equal to our line current. That's the first observation, that our line current is square root of 3 times larger than. Now, notice that our line current has phase shift associated with it. Alright? So, all the phasors were rotating in counterclockwise direction, which they would, according to international standard, were all rotating in counterclockwise direction. We will see the line current as a 30 degrees phase shift. So, number 2, line current has 30 degrees phase shift with respect to phase current. So, that's all about part 5B. Introduction to Delta-Wye transformer connection, part 5C. This part will continue to do a phasor analysis and look at what the relationship is between line current and phase current. In the last part, we look at phasor analysis between line current A and phase current A, niya ang phase current C. And nakita nato ang line current A is compared to phase current A na siya magnitude difference of square root of 3. And there's a phase difference of 30 degrees between sa duha ka currents. So in this video, let's look at the relationship between line current B and phase current B and see if we get the same relationship. Okay, so we're going to analyze this particular equation. So we know that line current B, which is current here, is equal to phase current B, and which is going to winding B, phase current B minus phase current A, which is coming from winding A. Now the reason why the equation is set up like this, it's because our delta connection is set up in a particular fashion, where the polarity side of winding B is connected sa ato node B1, and the non-polarity side of winding A is connected sa ato node B1. Let's evaluate sa ato equation. Alright, so we have a balanced system like we did like in our previous example. Mo na ito gibuhat sa previous example. So ato siya ibutang sa phase C back, ang phase C kung asa siya, and here is phase A at 0 degrees mark and defined by this particular equation. And mo na ito phase B with 240 degree mark and defined by this particular equation, and phase C which is at 120 degree mark and it's defined by this equation. Now this is what we call a balanced system. And this, so na video ana. Okay, so we're going to evaluate this equation here. Line current B is equal to phase current B minus phase current A. So what we're going to do is we're going to pick up phase current A and add it to the head of phase current B. Now the resultant vector would equal phase current B plus phase current A. Now that's not what we want. We want phase current B minus phase current A. So we would have to take current A, pick up and rotate it 180 degrees. Equal siya sa phase current A. And our resultant vector will start at the origin and the end of the tip of negative A. And the resultant vector equals phase current B minus phase current A. And the essential equal line current B. Right, so our line current B, the magnitude of line current B is the square root of 3 times phase current B. Very similar to our last example in part 5, right? And our line current B is also 30 degrees, lagging compared to phase current B. Now it's lagging because all the phasors, they are all rotating in counterclockwise direction. So phase B is ahead of line current B, right? So you rotate in counterclockwise direction. So 30 degrees is the phase difference between those phasors, right? So very similar to part 5B. Let's evaluate this evaluation very quick. Our line current C, which is our current here, is equal to phase current C, which is current going to phase C winding minus phase current B, which coming winding B into node C1. So you see that? We're going to evaluate this particular equation now. So what we'll do is we'll leave this line current B as it is. But we'll make a copy of phase B and we'll put here at the head of phase C current. But we'll have to rotate it 180 degrees because it's negative. So it's right here. So we're going to label this negative phase current B. The resultant vector is going to start at the origin and the end at this tip here. And the resultant vector equals C minus phase current B, right? So comparing it to phase current C, our resultant vector, which is our line current C, our line resultant vector is the square root of 3 larger than phase current C. Alright, you see that? As they all rotate in counterclock direction, there's a 30 degrees phase shift between phase current C and line current C. Okay, so we're saying essentially is the line current C, which is going to node C1. If we compare line current C with phase current C, which is going into winding C of our delta connected transformer, we'll see that the line current is square root 3 times larger than this particular phase current. So our line current also has 30 degrees phase shift for this delta connection. Compared to this particular phase current, phase C current is returning back our phasor diagram. Now in this diagram, I quickly redraw our line current A like we did in part 5B. So this is complete phasor diagram. So we see phase A current is here, phase B current is here, and phase C current is here. And in the blue is the current A. And this is line current B and this is line current B. We'll see that the line current have the same magnitudes. The line current also have 120 degree phase difference each of them. So we have 120 degrees difference here, 120 difference here, and 120 degree difference here. Okay, and all of them have the same magnitude, which is the square root of 3 times the phase current. In this example, we'll see that the line current is balanced of 3 phase current. And we see very clearly that the line current lag the phase current by 30 degrees. And all line current lag the phase current by 30 degrees. So that's all for part 5C. Thank you for watching and listening. Please subscribe. Thank you.